To understand this so-called HR diagram, we have to recall the various methods of stellar classification first. So far, we've covered the star's peak wavelength, color, and temperature as individual classification methods, but each of these is very much involved with the others. We've also talked about apparent and absolute magnitudes of stars and their spectral types. And as we said in the previous video, there are many more methods that we could use to classify stars, as we'll see now. One thing to note before we dive into the HR diagram is a quick clarification between luminosity and intensity. We've thrown both words around to discuss the brightness of stars, but here's the thing. We talked about the brightness of stars earlier in terms of their apparent and absolute magnitudes, but how bright we see the stars versus how bright they actually are is an entirely different concept. How bright a star actually is depends on a couple of things. One, how intense is the light that comes from that star? Is there a lot of light coming from a single unit of surface area or just a little? The amount of light energy emanating outwards per unit area per second from the surface of a star is the intensity of that starlight. The star's luminosity, however, is the total light energy output of the star per second. So every single unit of surface area is emitting the same amount of intense light, just now across the whole star's surface rather than that one single patch. So luminosity is the product of intensity and surface area. Now this is important to keep in mind since luminosity pops up on the HR diagram, but before we go on, what is the HR diagram? Named after Danish astronomer Einar Hertzsprung and American astronomer Henry Norris Russell, it is a graph of the brightness of stars versus their spectral types. Brightness can mean either the luminosity of the star or its absolute magnitude, and you're likely to see both on the HR diagram. And remember, spectral type can tell us the temperature and color of the stars as well, so we sometimes refer to the HR diagram as a color magnitude diagram. Now let's say we have a whole list of stars and we know a bit of information about them, like their spectral types and their absolute magnitudes. This is enough information to get started on looking for a pattern among the star's characteristics. If we plotted them on a two-dimensional graph, we can see that there might be some sort of trend between their spectral types and their absolute magnitudes. So let's start by labeling the x-axis as the spectral type and the y-axis as the absolute magnitude of the stars. Then we can use simple dots to represent the spot on this graph that the star's characteristics will intersect. For example, for the first star, star A, we have a spectral type of K2 and an absolute magnitude of -1. So we're looking at this point here, and that's where we'll place a dot for star A. Star B will be plotted here, and star C, which is an O3 type star with an absolute magnitude of 12, will be placed right here. Star D will go here and star E here, and we can continue plotting each of the remaining stars until we populate the entire graph at the center. But it's hard to tell whether there actually is any sort of common trend for the spectral types and the absolute magnitudes of these stars, unless we graph a whole lot more. Now we can see that there are some sort of patterns forming here. This is the HR diagram. This one in particular was made by Richard Powell with 22,000 stars from the Hipparcos catalog and another 1,000 from the Gliese catalog of nearby stars. So let's break this down. Well, first things first, what are the axes here? On the left, we have the visual luminosity of the stars as compared to the sun. On the right, we have the absolute magnitude of these stars. You may sometimes see these axes switch places, but that won't change the overall shape of the graph. It could happen though, and if it does, all the numbers on each axis will move to the other side as well. We'll see examples of the HR diagram in this format later in the video, but for now, let's continue. The horizontal axes are generally the spectral class of the stars and their temperatures. You may sometimes also see an axis with the color values, but we won't be using or needing that in this class, so you can practically ignore it as we work through this HR diagram. If we don't have color on the x-axis below, then chances are that the spectral class and the temperature axes will be separated with one on top of the HR diagram and the other on the bottom. The first feature of the HR diagram we'll look at is the one you're most likely already looking at. This diagonal feature that stretches across the HR diagram from the bottom right to the top left is called the main sequence. It's called as such because, well, it's the most prominent feature on the diagram, with most of the 23,000 stars in this HR diagram falling sequentially into this diagonal feature. In fact, about 91% of the stars in our local neighborhood are considered main sequence stars. These main sequence stars have a luminosity class of 5. And these luminosity classes, which are part of the Yerkes spectral classification, are usually presented in Roman numerals. Our Sun is an example of a main sequence star. Specifically, it is a G25 main sequence star. Sirius, the brightest star in the night sky, is also a main sequence star, classified as an A15, not A1V, though that's tempting to say, type star. The next most obvious grouping is just off to the right of the main sequence. These are the giants. They are big, bright, and cool-temperatured stars. These stars are huge, and they have a luminosity classification of class 3. Aldebaran is a great example of a giant star. With its spectral classification of type K53, we can see its size in comparison to our own Sun. And in fact, our Sun is headed towards becoming a red giant itself eventually, but not for another 5 billion years or so. We'll explore the eventual fate of our Sun later in the unit covering stellar evolution. The next feature of the HR diagram we'll look at is at the very top of the plot. Here we can see a few dots representing these supergiants, stars that are bigger and brighter than the giants. These stars have a luminosity classification of class 1 with subcategories A or B. A more luminous supergiant has a luminosity class 1A, and a less luminous supergiant will be of luminosity class 1B. Both Rigel and Betelgeuse in Orion are examples of supergiants, and we can see them both here in this image, along with Aldebaran from before, and Antares, another supergiant. Supergiant stars can be really, really big, like VY Canis Majoris, or UY Scuti, or Stephenson 218, all of which are potentially the largest known stars to date. Even higher up from the supergiants are the hypergiants. Now, these are extremely rare, extremely large, extremely bright stars, brighter than the supergiants. They are so bright that they have a luminosity class of 0 or 1A+. V915 Scorpii is an example of one such hypergiant with its spectral type of K01A0. As we move back down the HR diagram, we arrive at our next stopping point between the supergiants and the giants. Welcome to the realm of the bright giants, stars that are slightly bigger and brighter than the giants, but not as big or bright as the supergiants. Their luminosity class? Well, between the supergiants and giants, the bright giants have a luminosity classification of, you guessed it, 2. Canopus, the second brightest star in the night sky just below Orion, is a bright giant with a spectral classification of type A92. Other features of the HR diagram include the subgiants, which are located just above the main sequence and just below the giants, meaning that they are bigger and brighter than the main sequence stars, but not as big or bright as the giants. These subgiants are classified as luminosity class 4, being between two groups that are classified as 3 and 5. And last but not least, we also have a portion of the HR diagram that shows a decent population of stars with similar characteristics like high temperature and low luminosity. These are the white dwarf stars. They are smaller and dimmer than the main sequence stars, but their temperatures are high. They are hotter than the Sun, but can have temperatures comparable to the bigger, brighter, and hotter stars that we would find in the upper left corner of the HR diagram. White dwarfs have a luminosity class of 7. Let's look at some of the stars on the HR diagram now and try to make some sense of their similarities and differences based on where they appear on the HR diagram. Two stars can have the same temperature but different luminosities. This happens because the stars are very different in size. The more surface area that a star has, the more light energy that it can emit. So if two stars have the same temperature, but one is significantly brighter than the other, it's because it's bigger. Take, for example, Gliese 229a, a main sequence red dwarf star whose spectral class is type M1 and its temperature is 3600 Kelvin. Its luminosity is only 2% of the luminosity of the sun, so it's very, very dim. Now compare that to Betelgeuse, whose spectral type is also M1 or M2 depending on the source, and who has a temperature of also 3600 Kelvin. But its luminosity is almost 126,000 times brighter than the sun, which was already 50 times brighter than Gliese 229a, which means that Betelgeuse is 6.3 million times brighter than Gliese 229a. We'll use this annotated HR diagram for the next few examples. Two stars can have similar brightnesses, but their temperatures can vary drastically. For example, Achernar and Delta Cephei have almost the same luminosity and absolute magnitude, but their temperatures and spectral classes are significantly different. In fact, let's find out. How much hotter than Delta Cephei is Achernar? Well, Achernar's temperature is about 25,000 Kelvin, and Delta Cephei measures in at around 6,300 Kelvin. So Achernar is just about 4 times hotter than Delta Cephei. Similarly, Rigel and Regulus are two stars with almost the same temperature and spectral class, but their luminosities are significantly different. How much brighter than Regulus is Rigel? Well, Rigel has a luminosity of 100,000 solar luminosities, meaning it's 100,000 times brighter than the sun, and Regulus is almost 100 times brighter than the sun. So if we divide Rigel's luminosity by Regulus's luminosity, we'll see that Rigel is about 1,000 times brighter than Regulus. But what about the stars on the main sequence itself? Is there anything that can be said about the brightness and temperatures of these main sequence stars? As it turns out, yes, there is. Towards the top left of the main sequence and of the HR diagram in general, we have hot and bright stars, and generally these are big stars as well. Towards the bottom right, we have stars that are cool, small, and dim. So if we move along the main sequence from the bottom right to the top left, not only do these stars become brighter and hotter as you go, they actually get bigger too. Which brings us to our next concept, the mass-luminosity relationship. We'll see more about that in the next video.